Hello there, and welcome to The Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into something both fascinating and slightly unsettling: the strange, almost unbelievable behaviour of reality itself as revealed by quantum physics. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the nature of reality together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Tonight, we're going to explore a question that has quietly troubled some of the greatest minds in science. A question that doesn't shout but lingers, like a faint echo in a long hallway. What if reality doesn't fully exist until it is observed? At first, that might sound like the kind of idea you'd hear in a late-night conversation, somewhere between philosophy and science fiction. But strangely enough, it comes not from imagination, but from careful experiments, repeated, verified, and deeply puzzling. We will move slowly through this landscape. There's no rush. We'll begin with the world as it appears, solid, predictable, familiar. And then, almost gently, we'll notice the edges begin to blur. The rules that once felt certain will soften. And in their place, something quieter, more fluid, begins to take shape. Not chaos, but possibility. And as we explore, you might notice something curious. The deeper we look, the less the universe feels like a fixed stage, and the more it begins to resemble a story still being written. So let your thoughts settle, let your breathing slow, and together, let's step into a world where reality is not quite what it seems. There is a quiet comfort in the way the world usually behaves. If you pick up your phone and gently toss it into the air, you don't hesitate. You already know what will happen. It will rise, slow down, pause for just a moment and then fall back into your hand. Not because you hope it will, but because it must. This quiet certainty is something we rarely stop to notice. It sits beneath everything we do, like an invisible floor supporting each step. When you place a cup on a table, you expect it to stay there. When you walk across a room, you trust the ground will not suddenly disappear beneath you. This is the world of classical physics, a world where events follow clear paths, where causes lead to effects, where, if you know enough about a situation, how fast something is moving, how heavy it is, where it begins, you can predict what will happen next with remarkable precision. It is, in many ways, a deeply reassuring system. For centuries, this way of understanding the universe worked beautifully. From the motion of falling apples to the orbit of distant planets, this same set of rules seemed to apply everywhere. The universe appeared to be a vast, intricate machine, but one that could be understood, measured, and with enough patience, predicted. There is something almost calming about that idea. Imagine standing beside a quiet lake early in the morning. The surface is still, like glass. If you toss a small pebble into the water, ripples spread outward in smooth, predictable circles. Each wave follows the last, expanding gently, never surprising you. This is how classical physics sees the world. Every action creates a response. Every movement leaves a trace, and if you could watch closely, enough, you would never be caught off guard. But there is something we often forget. This sense of certainty comes not from the universe itself, but from the scale at which we live. We are large compared to the smallest building blocks of reality, and because of that, we experience a version of the world that feels stable, continuous, and well-behaved, like watching a film from far away where everything appears smooth, even though it is made of individual frames. Now, imagine moving closer, closer still, until you're no longer watching the ripples on the lake, but the individual molecules of water themselves. At that level, something strange begins to happen. The neat, predictable patterns begin to soften. The clear lines between cause and effect start to blur, and the quiet certainty that once felt so reliable begins to slip, just slightly, through your fingers. It's not that the rules disappear, it's that they change. There is a moment almost imperceptible where the world transitions from something solid into something more like a question. Not a loud question, not one that demands an answer, but a gentle uncertainty sitting just beneath the surface, and for a long time no one noticed. Because for everything we could see, touch, and measure, classical physics worked perfectly. It guided ships across oceans, predicted eclipses, and eventually helped humanity reach beyond the Earth itself. It seemed complete. Until quietly, experiments began to reveal something unexpected. At first, the results were small, easy to overlook, tiny inconsistencies that didn't quite fit the established picture. But as scientists looked closer, these inconsistencies didn't disappear. They grew. And with them came a realization that must have felt deeply unsettling. The rules we trusted were not the full story. Somewhere beneath the familiar surface of reality, there existed another layer, a deeper structure, one that did not follow the same comforting patterns, a layer where certainty gave way to possibility, where objects did not always have a single definite state, where in some sense things could be more than one thing at once. It's difficult to describe this shift in a single moment because it didn't arrive all at once. It unfolded slowly like a fog rolling in over that quiet lake, softening the edges of everything it touched. At first, you might not even notice it, but then, gradually, the shoreline disappears, the reflections blur, and the world that once felt so clear becomes something more mysterious, more open, and perhaps just a little more fragile. What makes this especially strange is not just that the rules change, it's that they change in a way that challenges something very deep in us, our intuition. We're used to thinking of reality as something that exists independently of us, a stage that remains steady, whether we are watching or not. The moon is still there when you close your eyes. The room does not rearrange itself when you leave. This assumption feels so natural that we rarely question it. And yet, as we move deeper into the quantum world, this assumption begins to feel less certain. Not wrong, exactly, but incomplete. It's as if the universe is gently suggesting that what we see is only part of the picture, that beneath the surface of everyday experience lies something more subtle, something that does not fully reveal itself unless we look in just the right way. And even then, what we find may not behave the way we expect. So for now, just let this idea settle. The world you experience each day, solid, predictable, dependable, is real. But it may not be the whole of reality. It may be more like a calm surface, beneath which something far more fluid is quietly unfolding, something that does not follow the same rules, something that, in certain moments, seems to wait, before deciding what it truly is. And as we continue, we'll begin to explore that deeper layer together, not all at once, but gently, piece by piece, allowing the familiar to slowly give way to the unknown. There is a certain moment, subtle and easy to miss, when certainty begins to loosen its grip, It doesn't happen with a loud crack or a dramatic shift. Instead, it feels more like a quiet hesitation, as if the universe itself pauses just for a fraction of a second before continuing on. For a long time, scientists believed that if something appeared uncertain, it was only because we didn't yet have enough information. If a system behaved unpredictably, then surely, given enough measurement, enough precision, enough patience, it would eventually reveal a clear and definite answer. This belief was not unreasonable. In fact, it worked beautifully. If you watch the motion of a pendulum, for example, you can predict exactly where it will be at any given moment. If you know how fast a planet is moving and how far it is from the sun, you can trace its path across the sky years into the future. Everything seemed to follow a quiet, dependable rhythm. But then, as scientists began to study smaller and smaller pieces of the world, tiny fragments of matter, far beyond what the eye could see, this rhythm began to falter. Not completely, just enough to raise a question. At first, the behaviour of these tiny particles didn't seem alarming. They still moved, still interacted, still followed patterns. But those patterns were softer, less certain, as though the universe had traded sharp lines for gentle gradients. Instead of saying, "This is exactly where the particle is," the best answer became, "It is likely to be somewhere around here." Instead of certainty, there was probability. Now, probability is not unfamiliar to us. We use it all the time. If you flip a coin, you don't know whether it will land on heads or tails, but you know the chances are roughly equal. If you roll a die, you expect any number from 1 to 6, each with the same likelihood. But here is the crucial difference. In everyday life, the uncertainty comes from ignorance. The coin already has a definite outcome as it spins through the air. We just don't know it yet. But in the quantum world, something far stranger seems to be happening. The uncertainty is not just in our knowledge, it appears to be in reality itself. This idea was deeply unsettling, even to the physicists who first encountered it. Among them was the brilliant and often playfully honest Richard Feynman, who once admitted in a tone that was both humble and slightly amused that no one truly understands quantum mechanics, not because it is poorly explained, but because it refuses to fit into the ways we expect the world to behave. Imagine standing in that same quiet room as before. You toss your phone into the air again, but this time, instead of following a single smooth path, its motion becomes uncertain, not wildly chaotic, just ambiguous. Perhaps it rises and falls as expected, or perhaps it drifts slightly to the left, or perhaps in some strange sense it is not committed to any one path at all. Now, of course, in our everyday world, this does not happen. The phone follows a single trajectory. The outcome is clear. But at the smallest scales of reality, something like this ambiguity is not only possible, it is fundamental. To understand this, it can help to imagine a different kind of landscape. Earlier, we spoke of a calm lake, where ripples spread in predictable circles. Now picture that same lake, but covered in a soft morning mist. You can still see the water, you can still sense the movement, but the edges are no longer sharp. The boundaries between one ripple and the next begin to blur. And if you try to point to a single exact location, you find yourself gesturing instead to a region, a possibility, rather than a precise point. This is how quantum mechanics begins to describe the world, not as a collection of fixed objects moving along definite paths, but as a set of possibilities gently overlapping and interacting, like waves crossing one another on the surface of water. And just like waves, these possibilities can combine. They can reinforce each other, making certain outcomes more likely. Or they can cancel each other out, making other outcomes less likely, or even impossible. The language used to describe this is mathematical, of course. It involves careful calculations of probabilities and patterns. But when translated into something more intuitive, it becomes a picture of reality that is less like a solid structure, and more like a shifting dynamic field of potential. A place where things are not simply this or that, but sometimes a blend of both, waiting in a quiet and patient way for something to tip the balance. And this is where a deeper question begins to emerge. If reality is made of possibilities, then what causes one possibility to become real? What turns a gentle cloud of potential into a single definite outcome? At first, it might seem like the answer is straightforward. After all, in everyday life, things become real all the time. You make a choice, you take a step, you pick up a cup, and the world responds accordingly. But in the quantum world, the transition from possibility to reality is not so simple. It does not happen gradually. It happens suddenly, almost like a decision. And yet, there is no clear decision maker. This is where many physicists began to feel a quiet sense of unease, because the deeper they looked, the more it seemed that reality itself was not fully settled until something happened. Something that forced it to settle. And that something, as we will soon explore, has a curious and intimate connection to the act of observation. Not observation in the sense of human awareness or conscious thought, but in the sense of interaction, of contact, of one part of the universe gently touching another, and in doing so, shaping what becomes real. It is a delicate idea, one that doesn't shout or demand attention, but instead lingers softly at the edge of understanding. The universe, it seems, may not be a fixed stage upon which events unfold. It may be something more fluid, something that waits, something that holds many possibilities at once, like a story not yet fully written, where the next line has not been chosen, and when that choice finally comes, it does not feel random in the usual sense. It feels inevitable somehow, as though the possibility had always been there, quietly waiting for its moment to become real. So as you rest here, listening, you might begin to notice a gentle shift in perspective. The solid ground of certainty has not disappeared. It is still there, supporting the world you know. But just beneath it, something softer is beginning to reveal itself. A layer where outcomes are not fixed, where paths are not singular, where the universe, in its quiet and patient way, seems to hold its breath just before deciding what it will be. And as we continue, we'll move a little closer to that moment, the moment where possibility narrows and reality gently takes shape. There is a simple image that can help us step a little deeper into this strange landscape. Imagine holding a coin between your fingers. You flip it gently into the air, watching it spin. For a brief moment, it is neither heads nor tails. It turns, it glints in the light, it dances between two possibilities, but only for a moment. Soon enough, it lands, and the uncertainty disappears. It becomes one thing or the other, heads or tails. This is how we usually think about uncertainty. There is always a definite answer waiting beneath the surface. Even while the coin is spinning, we assume that if we had perfect knowledge, perfect timing, perfect measurement, we could predict exactly how it would land. The uncertainty is only temporary, a reflection of our limited perspective. But now, gently set that familiar idea aside. Because in the quantum world, the coin behaves differently. It doesn't just spin on its way to a hidden outcome. It does something far more subtle. It exists in a quiet and almost impossible way, as both heads and tails at the same time. Not because we don't know the answer, but because, in a very real sense, the answer has not yet been chosen. This is the idea of superposition. It is one of the most central and most unsettling features of quantum mechanics, and like many things in this field, it is easier to feel than to define. So rather than thinking of it as a technical concept, imagine it as a kind of gentle overlap, a blending of possibilities, a state where reality has not yet committed to a single outcome. You might picture it like a melody that has not yet resolved, a chord hanging softly in the air, containing multiple notes at once, waiting for the music to move forward, or like a path in a foggy landscape where several directions are possible, but none have been chosen. In this state, the quantum system is not switching rapidly between options. It is not secretly one thing or the other. Instead, it holds all allowed possibilities together as a unified whole. And this is not just a poetic way of speaking. Experiments consistently show that particles, tiny pieces of matter or light, behave as though they are exploring multiple possibilities simultaneously, as though they are not confined to a single path, but instead spread out, like ripples moving across water. Now, it's important to pause here, just for a moment, and notice something. This idea does not fit comfortably within our everyday experience. You have never seen a coin that is both heads and tails. You have never held a cup that is both on the table and not on the table. The world you move through each day feels solid, definite, and well-defined, and yet beneath that familiar surface, this softer, more fluid behaviour appears to be fundamental. It is not an exception, it is the rule. To make this a little more tangible, imagine a beam of light entering a room filled with many possible paths. In our classical view, the light would choose one route and follow it, a single trajectory clearly defined. But in the quantum picture, the light behaves differently. It is as though it gently explores all available paths at once, not by splitting into pieces in the way we might imagine, but by existing as a spread of possibilities, each one contributing to the final outcome. Some of these possibilities reinforce each other, making certain results more likely. Others cancel out, fading quietly into impossibility. And what we observe at the end is shaped by this entire web of overlapping potential. This is why superposition is so powerful. It is not just about being in two states at once. It is about the idea that reality, at its deepest level, is not built from single, definite events, but from a kind of quiet interplay between many possibilities. Now, if you stay with this idea for a moment, a natural question begins to form. If something can exist in many states at once, what causes it to become just one? What makes the coin finally land? Because eventually it does. In every experiment, no matter how strange the behaviour is along the way, the result we observe is always definite. The particle is found here, not there. The outcome is this, not that. The soft cloud of possibilities seems to collapse into a single point of reality. And this transition, this gentle narrowing from many to one, is where things begin to feel truly mysterious. Because it does not happen gradually. It happens suddenly, almost like a decision being made. But again, there is no clear decision maker. There is no visible mechanism that reaches into the cloud of possibilities and selects one outcome over the others. There is only the quiet fact that when we look, or more precisely when an interaction takes place, the possibilities resolve, they settle, and one version of reality emerges. It's tempting to imagine that the particle chooses a state, or that something forces it into place. But these are just metaphors, soft ways of pointing towards something that resists clear description. What we can say, gently and carefully, is this. Before interaction, the system exists as a range of possibilities. After interaction, it appears as a single, definite outcome. And between those two states lies one of the deepest questions in all of physics. This is the beginning of what is often called the measurement problem, though we won't give it that name just yet. For now, it's enough to feel the shape of it. A world where things are not fully decided until something happens. A world where reality is not entirely fixed, but waits, quietly, patiently, before settling into form. If you let your thoughts rest here for a moment, you might notice how different this feels from the solid, predictable world we began with. Earlier, everything followed clear lines. Causes led to effects. Objects had definite properties, whether or not we were paying attention. But now those lines have softened, the boundaries have blurred, and in their place, we find something more open. A kind of gentle uncertainty that does not feel chaotic, but alive with possibility. It is not that the universe has become random, it is that it is no longer entirely decided. And as we continue, we will begin to explore what happens when this delicate state of possibility meets something else, something simple and yet deeply powerful, the act of observation. Not in the sense of watching with your eyes, but in the sense of interaction, of contact, of one part of the universe brushing against another, and in doing so shaping what becomes real. And it is there, in that quiet moment of contact, that the coin, after all its gentle spinning, finally softly comes to rest. Time equals, quote, 3 seconds, quote, / greater than. There is a certain kind of idea that doesn't try to explain the world, but instead reveals how strange our explanations have become. One of the most famous examples of this comes from the physicist Erwin Schrodinger, who, in the 1930s, proposed a thought experiment so unusual that it has quietly lingered in the imagination of scientists and curious minds ever since. You may have heard of it before. A cat, a box, a fragile connection between life and death. But what is often missed is that this idea was never meant to be taken literally. It was not designed to suggest that cats can exist in 2 states at once. It was, in fact, a gentle form of protest, a way of pointing out just how uncomfortable the implications of quantum mechanics truly are. So let's step into the thought experiment, slowly, and allow it to unfold. Imagine a sealed box. Inside there is a cat. Alongside the cat is a small device connected to a single quantum event, something that happens at the smallest scale of reality. It might be the decay of a tiny particle, an event that is fundamentally unpredictable. If that tiny event occurs, the device releases a poison, and the cat does not survive. If the event does not occur, nothing happens, and the cat remains alive. Now, here is where the quiet tension begins. In the quantum world, before any interaction takes place, that tiny event does not have a single, definite outcome. It exists in a state of superposition, holding both possibilities at once. The event has happened, and it has not happened. And because the fate of the cat is directly tied to that event, the entire system, the particle, the device, and the cat becomes entangled in that same uncertainty. So before the box is opened, the cat is described as being both alive and not alive at the same time. Not because we lack information, but because, according to the theory, reality itself has not yet settled into one outcome. Now, if you pause here, you may feel a quiet resistance to this idea. It doesn't sit comfortably. A cat cannot be both alive and not alive. The world does not work that way. There is something in us that instinctively pushes back, that insists on a clear answer, and that reaction, that discomfort, was exactly the point. Schrodinger wasn't trying to prove that the cat exists in 2 states. He was trying to show that if we take the rules of quantum mechanics and apply them directly to the everyday world, we arrive at something that feels deeply unreasonable, almost absurd. It is as if the theory, when stretched beyond its natural domain, begins to reveal its own strangeness. But here is where things become even more interesting. Because despite the discomfort, the underlying principles of quantum mechanics continue to hold true in experiment after experiment. At the level of tiny particles, superposition is not just a strange idea. It is something we can observe indirectly, something that shapes the outcomes we measure. So the question becomes, where is the boundary? At what point does the soft, overlapping world of possibilities give way to the solid, definite world we experience each day? Is there a clear dividing line between the quantum and the classical? Or is the difference simply one of scale, of complexity, of how many parts are interacting at once? Imagine for a moment that instead of a cat we consider something smaller, a single particle, isolated as much as possible from its surroundings. In that quiet isolation, it can maintain its delicate state of superposition, holding multiple possibilities together like a fragile balance. But as soon as it begins to interact with its environment, with air, with light, with anything at all, that delicate balance starts to break. The possibilities begin to narrow. The system settles into a single outcome, not because someone is watching in the human sense, but because interaction itself, contact, seems to gently force reality to choose. And this brings us to a subtle but important shift in perspective. When we speak of observation in quantum mechanics, we are not talking about awareness, or thought, or perception. We're talking about interaction, about one part of the universe influencing another, a photon of light touching a particle, a measuring device registering a result, a tiny exchange of energy that leaves a trace. These are the moments where possibility begins to resolve into reality. So the cat in the box is not waiting for a human to open the lid in order to become alive or not alive. The system is constantly interacting, constantly evolving, and through those interactions it gradually loses its delicate superposition. And yet the thought experiment remains powerful, because it captures something essential. It shows us that the line between possibility and reality is not as sharp as we once believed, that under certain conditions, the world does not commit to a single story right away. Instead, it holds multiple stories at once, and only through interaction, through connection, does one of those stories become the one we experience. There is a quiet beauty in this idea, even if it feels unsettling. It suggests that reality is not a rigid structure, fixed and unchanging, but something more dynamic. Something that unfolds moment by moment as possibilities gently give way to outcomes. Like a story being written in real time, not all at once but line by line. And if you listen closely, you might begin to sense that this is not just a strange feature of distant particles or sealed boxes. It is a glimpse into something deeper, a hint that the certainty we experience in everyday life is not the starting point of reality, but its result. That beneath the surface of the familiar world lies a quieter layer, one where things are not fully decided, where possibilities linger, and where the act of interaction plays a subtle but essential role in shaping what becomes real. So as you rest with this idea, let it remain soft. There's no need to force it into something rigid or fully understood. For now, it is enough to notice the feeling it creates, a gentle shift, a quiet awareness that the world may be less fixed than it appears, and more open, more fluid than we once imagined. And as we move forward, we will begin to explore that moment of interaction more closely. The moment when the many becomes one. The moment when possibility settles into reality. There is a moment, so ordinary that we rarely notice it, when something uncertain becomes clear. You reach for your phone in a dim room. At first it is only a shape, a suggestion in the darkness. But as your eyes adjust or as you turn on a light, the outline sharpens. The object seems to settle into place, becoming definite, familiar, real. It feels as though The act of looking reveals what was already there, and most of the time, that is exactly how the world behaves. But in the quantum world, this simple idea becomes far more delicate, because there, looking does not simply reveal reality, it helps define it. Now, it's important to be gentle with this idea, because it is often misunderstood. When we say that observation shapes reality, we're not saying that human awareness controls the universe. The world does not wait for your eyes to open in order to decide what it will be. Instead, something quieter is happening. In quantum physics, observation means interaction. It is the moment when one part of the universe comes into contact with another, exchanging a small amount of energy, leaving a trace, creating a record. This could be a particle of light touching an electron. It could be a measuring device registering a signal. It could be any physical process that connects a system to its surroundings. And it is in these moments of interaction that something subtle unfolds. Before the interaction, the system exists as a spread of possibilities, not fixed, not singular, but gently holding multiple potential outcomes at once, like a soft cloud with no sharp edges. After the interaction, that cloud seems to gather itself. It narrows, it settles into a single, definite state. This transition is often described using mathematical language, but we can feel it in a simpler way. Imagine looking at a photograph that is slightly out of focus. The details are blurred, the edges soft. You can sense what is there, but not precisely. Then, with a small adjustment, the image sharpens. The blur resolves into clarity. The possibilities collapse into a single crisp picture. In the quantum world, something like this appears to happen when interaction takes place. The system chooses a definite outcome, not gradually but all at once. And this is where the quiet mystery deepens. Because we do not fully understand why this happens, we can describe it. We can predict the probabilities of different outcomes. We can perform experiments that confirm the results again and again. But the underlying reason, the mechanism that turns possibility into reality, remains hidden. It is as if we are watching a story unfold, knowing how each chapter is likely to end, but not quite understanding how the story itself is being written. This is often called the measurement problem, though the name feels almost too simple for something so profound. It is not just a technical question. It is a question about the nature of reality itself. When does something become real? Is it real before interaction, existing in some undefined way? Or does reality, in some sense, emerge through the act of interaction? There is no single answer that satisfies everyone. Some interpretations suggest that the possibilities were always there, waiting to be revealed. Others suggest that reality itself is not fully formed until that moment of contact. And still others propose that all possibilities continue to exist, each in its own quiet branch of reality, even after we observe just one. For now we don't need to choose between these ideas. It is enough to notice the shape of the mystery, a world where things are not fully settled, where the act of interaction plays a central role, where the boundary between what is possible and what is real is not as clear as we once believed. To make this a little more tangible, imagine standing in a room filled with many doors. Each door represents a possible outcome. Before you move, all the doors are open, all paths are available. The space feels wide, undefined, full of potential. But the moment you take a step, any step, you begin to close off other possibilities. The act of choosing one path narrows the field, leaving behind a single direction, a single experience. In the quantum world, interaction plays a role similar to that step. It does not simply reveal which door was already chosen. It helps define which door becomes the path forward. And yet, there is something else to notice here. Even though the underlying process is uncertain, The outcomes we observe are not chaotic. They follow patterns, carefully measured patterns. If we repeat the same experiment many times, we do not get completely random results. Instead, we see distributions. Some outcomes appear more frequently than others, in a way that can be predicted with remarkable accuracy. It is as though the universe operates with a quiet statistical rhythm, not fixed outcomes, but consistent patterns of possibility. This balance between uncertainty and predictability is one of the most beautiful aspects of quantum mechanics. It suggests that while individual events may not be determined in advance, the overall structure of reality still holds a kind of order, a gentle order woven from probabilities. And this brings us back to the act of looking, not as a passive act, but as a moment of connection, a moment where the soft field of possibilities meets the rest of the universe, and in doing so becomes something definite. It's a quiet process, one that happens constantly everywhere at scales far beyond what we can see, and yet it shapes the very fabric of the world we experience. So as you sit with this idea, you might begin to feel a subtle shift. The world around you still feels solid, still dependable. The objects in your room remain where they are. The familiar rules continue to hold. But beneath that surface, there is a deeper layer, a layer where reality is not entirely fixed, where possibilities linger, where the simple act of interaction, so ordinary, so easy to overlook, plays a role in shaping what becomes real. And as we move forward, we will begin to explore what happens when this delicate interplay between possibility and observation reveals itself in experiment, when light itself begins to behave in ways that challenge everything we thought we understood. There is a kind of question that does not demand a quick reply. It lingers instead, like a soft echo, returning again and again, each time a little deeper than before. By now, you may feel it forming quietly in the background. If reality can exist as a range of possibilities, and if interaction causes those possibilities to settle into a single outcome, then what exactly is doing the settling? What is it that gently narrows the many into one? At first, it might seem like we've already answered this. We spoke about interaction, about the way one part of the universe touches another, and how that contact appears to shape what becomes real. But if you sit with it just a little longer, something begins to feel incomplete. Because interaction is everywhere. Particles are constantly touching, exchanging energy, influencing one another in ways both large and small. If interaction alone were the full answer, then perhaps reality should always be definite, always settled. And yet, in carefully controlled experiments, we still observe that delicate state of superposition, that soft cloud of overlapping possibilities, persisting, sometimes longer than we would expect. It is as if the universe is capable of holding its breath, capable of maintaining uncertainty, even in the presence of subtle interactions, until something more decisive occurs. And this is where the question deepens. Not just what causes reality to settle, but when. When does a system stop being a blend of possibilities and become a single, definite outcome? Is it the moment a particle of light touches it? Is it when a measuring device records a result? Or is it only when that result becomes part of a larger chain of events, written down, stored, shared? There is no clear boundary. And that absence of a boundary is what makes this question so quietly profound. In everyday life, we're used to clear transitions. Water freezes at a certain temperature. A switch turns a light on or off. A door is either open or closed. There is a sense of clean division, a point where one state becomes another. But in the quantum world, that line becomes blurred. There's no single moment we can point to and say, here, This is where possibility ends and reality begins. Instead, it feels more like a gradual shift, one that resists being pinned down. To explore this feeling, imagine watching the sky at dusk. At some point, day becomes night. But when exactly does that happen? There's no precise instant where you can say the transition is complete. The light fades slowly, gently, blending one state into another, and yet by the end the difference is unmistakable. The quantum transition from possibility to reality feels similar. We know it happens, we can observe the result. But the exact moment of change remains elusive. And so, physicists have proposed different ways of understanding this process. Some suggest that the transition is tied to the size of the system, that small, isolated systems can remain in superposition, while larger, more complex systems cannot. That, somewhere along the way, as interactions accumulate, the delicate balance of possibilities becomes too fragile to sustain. Others propose that all possibilities continue to exist, even after interaction, but that we experience only one of them. That reality does not collapse in the way we imagine, but instead branches quietly, each possibility unfolding in its own separate path. And still, others suggest that our current understanding is incomplete, that there is a deeper layer of physics not yet discovered that governs this transition in a way we cannot yet see. What is striking is that, despite decades of study, no single explanation has fully resolved the question. The mathematics of quantum mechanics works beautifully. It predicts outcomes with extraordinary precision. It allows us to build technologies that shape the modern world. And yet, when we ask what is really happening beneath those predictions, the answers become less certain. It is as though we have learned how to read the script of the universe, but not how the script itself is written. This realization can feel unsettling at first. We're used to the idea that deeper knowledge brings clearer understanding, that if we look closely enough, measure carefully enough, think deeply enough, the world will eventually reveal its secrets in a straightforward way. But here, at the foundation of reality, we encounter something different, a kind of quiet ambiguity, a suggestion that the universe may not be fully describable in the terms we're most comfortable with. And yet, there is also a kind of beauty in this, because it invites us to shift our perspective. Instead of asking for a single, definitive answer, we can begin to appreciate the richness of the question itself, the way it opens space for different interpretations, different ways of seeing, each one capturing a part of the whole. It becomes less about forcing the universe into a clear picture, and more about learning to sit with its subtlety, to feel the way possibility and reality coexist, not as opposites, but as parts of a continuous process, like waves and water, inseparable, each giving meaning to the other. And perhaps, in a quiet way, this reflects something deeper about how we experience the world. There are moments in life when things feel uncertain, not yet decided, paths that have not been chosen, outcomes that remain open. And over time, through action, through interaction, those possibilities settle into a single lived experience, not because they were predetermined, but because something, somewhere, gently tipped the balance. So as you rest with this idea, let it remain open. There is no need to resolve it. The question itself is enough. What causes reality to become real? Not in a dramatic sense, but in a quiet, unfolding way. And as we continue, we will begin to see how this question reveals itself, not just in abstract thought, but in carefully designed experiments, where light, of all things, begins to behave in ways that challenge everything we thought we understood, where possibility and reality dance together, and where even the simplest setup can reveal something deeply unexpected. There is a kind of experiment that feels so simple that you almost expect nothing unusual to happen. A flat wall, 2 narrow openings cut into it, and a gentle stream of tiny particles, little packets of light, moving toward those openings one by one. If you were to imagine this setup in your mind, you might picture something very straightforward. Each particle travels forward, reaches the wall, and passes through one of the 2 openings. Afterward, it continues on its way and lands on a screen placed behind the wall. And over time, as many particles arrive, you would expect to see 2 bright regions forming on that screen. One behind each opening, 2 clear lines, like footprints marking the paths the particles have taken. It feels obvious, almost too obvious to question. After all, if you throw small objects through 2 gaps, that is exactly what you would see. 2 clusters, each corresponding to one path or the other. No mystery, no ambiguity. And for a long time, that is what scientists expected as well. So they built this experiment carefully, precisely using particles of light. Tiny flashes released one at a time, moving toward those 2 openings. At first, everything seemed ordinary. Each particle left its source, travelled toward the wall, and eventually struck the screen behind it. A small point of light appeared where it landed, like a faint star in a growing constellation. One particle, then another, then another. Each arrival seemed independent, almost random in its exact position, but always somewhere behind the openings. If you stopped the experiment early, you might not notice anything unusual, just a scattered pattern of tiny dots. But if you allow the experiment to continue, patiently, letting thousands, then millions of particles arrive, something begins to emerge. A pattern, not 2 simple lines, but something far more delicate. Instead of 2 bright regions, the screen fills with a series of light and dark bands stretching across its surface. Bright areas where many particles arrive and darker areas where almost none do. It looks less like 2 clusters and more like a set of ripples, like waves spreading across water, overlapping and interacting. And this is where the quiet surprise begins, because waves behave in a very specific way. When 2 waves meet, they do not simply pass through each other unchanged. They combine. In some places, they reinforce one another, creating larger peaks. In other places, they cancel each other out, leaving calm, still regions behind. This pattern of reinforcement and cancellation creates those alternating bands, bright, dark, across the screen. And seeing this pattern suggests something remarkable. It suggests that each particle is not behaving like a tiny solid object travelling through just one opening. Instead, it behaves as though it has passed through both openings at once. Not in the sense of splitting into 2 smaller particles, but in the sense of existing as a spread of possibilities, exploring multiple paths simultaneously. You might picture it as a gentle ripple moving through both openings, overlapping with itself on the other side. And as those overlapping possibilities combine, they shape the final pattern that appears on the screen. Now, if you pause here, there is a subtle shift in perspective. We began with a simple expectation. Particles go through one opening or the other. But what we observe suggests something different. Each particle seems to carry with it not just a single path, but a range of possibilities, and those possibilities interact with each other, even though only one particle is present at a time. This is perhaps the most surprising part, even when the particles are sent one by one, so that there is never more than a single particle in the system, the pattern still emerges. Slowly, dot by dot, the same wave-like structure builds up on the screen, as though each particle is somehow aware of both openings, and of the pattern formed by all the particles that came before it. Of course, it is not awareness in any human sense. There is no thinking, no intention. only a deeper, more subtle behaviour that reflects the underlying nature of reality at this scale. And this behaviour aligns perfectly with the idea we explored earlier, that before interaction, a system does not exist in a single, definite state. It exists as a range of possibilities. In this case, the possibility of passing through one opening and the possibility of passing through the other. And rather than choosing one path immediately, the particle seems to move through both possibilities at once, allowing them to overlap and interact. The final pattern on the screen is not the result of many independent particles choosing paths randomly. It is the result of many overlapping possibilities gently combining over time, and when you look at the full pattern, you're not just seeing where the particles landed, you're seeing the shape of those possibilities, the quiet fingerprint of a world that is not entirely fixed. Now, there is something almost poetic about this. A single particle moving through space, carrying with it a spectrum of potential paths, each one contributing to the final outcome. It is as though the particle is not a point, but a kind of soft presence, spread across space, only becoming localized when it finally reaches the screen. And even then, the pattern it leaves behind tells a story of where it could have been, not just where it was. If you let your thoughts rest here for a moment, you might notice how this begins to challenge our usual sense of reality. We're used to thinking of objects as having definite positions, definite paths, definite histories. But here at this small scale, those certainties begin to loosen. The particle does not seem to follow a single path. It seems to explore many, and only at the end, when it interacts with the screen, does it settle into a single, definite point. This experiment, simple as it is, opens a quiet doorway into a deeper understanding. It shows us that reality, at its foundation, may not be built from fixed trajectories and solid paths. It may be built from possibilities. Possibilities that spread, overlap, and gently shape the outcomes we observe. And yet, there is one more layer to this story. Because as strange as this behaviour is, it becomes even more intriguing when we begin to ask a very simple question. What happens if we try to find out which path the particle actually took? It is a natural question. After all, if there are two openings, we might want to know which one the particle passed through, and it seems like it should be easy enough to answer. All we need to do is place a small detector near the openings, something that can quietly record the particle's path as it passes. A simple addition, a gentle act of curiosity. But as we will soon see, even this small change alters everything. If you let the image from before linger in your mind, the wall with two narrow openings, the quiet stream of particles, and the screen slowly filling with delicate bands of light and shadow, you may begin to feel a gentle shift in how you picture those particles. At first we imagine them as tiny objects, small solid points travelling through space, like grains of sand tossed through the air, each one following a path landing somewhere definite. But the pattern on the screen tells a different story. It does not look like the result of many tiny objects choosing between two routes. It looks like something softer, something more fluid, a pattern that seems to emerge from overlap, from combination, from a kind of quiet interaction between possibilities. And this is where the language of waves becomes helpful, not because light is exactly like water, but because the behaviour we observe shares a familiar shape. Imagine standing beside that calm lake again. You toss two pebbles into the water a small distance apart. Each pebble creates its own set of ripples spreading outward in gentle circles. At first, the ripples expand independently, but as they grow, they begin to meet. Where the peaks of the waves align, the water rises a little higher. Where a peak meets a trough, the movement softens and the surface becomes calmer. This dance of reinforcement and cancellation creates a pattern across the water, regions of motion, regions of stillness, arranged in a delicate repeating structure. Now, imagine that instead of water, you're looking at the screen in the experiment. The bright bands are like the places where the ripples reinforce each other. The dark bands are like the places where they cancel out. And the pattern as a whole reflects not just where something landed, but how different possibilities combined along the way. This is the key idea. The particle does not simply take one path. It behaves as though it explores multiple paths, and those possibilities interact with one another before the final outcome appears. It is as if the particle carries with it a kind of gentle wave, not a physical ripple in water, but a spread of potential ways it might move. And as this spread passes through both openings, it overlaps with itself. The possibilities from one opening meet the possibilities from the other, and together they shape the pattern we see. What makes this especially fascinating is that this wave-like behaviour is not limited to large groups of particles. Even when the particles are sent one at a time, the same pattern slowly builds up. Each individual particle leaves a single point on the screen. But over time, those points arrange themselves into the same series of bands, as though each particle is contributing to a shared pattern that emerges only when we step back and look at the whole. It is a bit like watching raindrops fall on a surface. Each drop lands in a specific place, but over time, a larger pattern begins to form, a reflection of underlying currents, shapes, and influences that are not visible in any single drop. In the same way, each particle seems to know, in some quiet sense, about the overall structure of possibilities, not through awareness, but through the way those possibilities are woven into the fabric of the system itself. And this brings us to a subtle but important point. When we say that the particle behaves like a wave, we're not saying that it is literally a wave in the classical sense. It does not spread out as a visible ripple you could touch or measure directly. Instead, what spreads is the range of possibilities, the different ways the particle could move, the different paths it could take, the different outcomes it could produce. All of these possibilities exist together, overlapping and interacting, until something happens to bring them into a single result. This is why the pattern on the screen is so revealing. It is not just a collection of impacts. It is a map of possibilities, a quiet record of how those possibilities combined, reinforced and cancelled each other before settling into the points we observe. And if you sit with that idea for a moment, you may begin to feel how different it is from the world we usually imagine. We tend to think of objects as having clear paths, clear histories, clear positions at every moment. But here, the path itself becomes uncertain, not hidden, but undefined. The particle does not simply travel from point A to point B along a single line. It exists in a sense as a blend of many possible journeys, all unfolding together until the final interaction occurs. There is something almost poetic about this, a single particle carrying within it a quiet spectrum of possibilities, moving through space not as a fixed point, but as a gentle unfolding of potential. And only at the end, when it meets the screen, does it become something definite, a single dot, a single outcome. But even then, the pattern formed by many such dots tells a deeper story. A story of overlap, of interaction, of a world that is not built from single paths, but from many possibilities gently weaving together. Now, as we rest here, there is a natural curiosity that begins to emerge. If the particle behaves like a wave, exploring multiple paths at once, then what happens if we try to observe those paths more closely? If we place a small device near the openings, something that can quietly tell us which path the particle takes, will the particle still behave like a wave? Will the pattern remain the same? Or will something change? It feels like a simple question. After all, in everyday life, Observing something does not usually alter its behavior in such a fundamental way. Watching a ball roll across the floor does not change its path. Looking at a cup on a table does not cause it to shift. Observation, in our experience, reveals what is already happening. But in the quantum world, as we're about to see, the act of asking a question can gently reshape the answer. And the moment we try to know which path the particle takes, the entire pattern begins to change. There is a quiet assumption we carry with us through everyday life, that observing something does not fundamentally change it. You can watch a bird fly across the sky, and its path remains the same whether you're looking or not. You can glance at a cup resting on a table, and it does not shift position simply because you noticed it. Observation in our familiar world feels passive. It reveals what is already there. But in the experiment we have been gently exploring, something different begins to unfold. We have a wall with two openings, a stream of tiny particles, and a screen that slowly fills with a pattern of soft alternating bands, light and dark like ripples frozen in place. That pattern, as we have seen, reflects a world where each particle behaves like a spread of possibilities, moving through both openings at once and allowing those possibilities to overlap. Now, imagine making a small change, not a dramatic alteration, just a subtle addition. You place a tiny detector near the openings, something delicate enough to notice which path a particle takes as it passes through. It does not interfere in any obvious way. It simply records information. Which opening did the particle go through? It feels like a simple question, and yet the moment you ask it, everything changes. When the experiment is run again, with this detector in place, the pattern on the screen begins to shift. The delicate bands of light and shadow fade away. In their place, two clear regions appear. Two clusters, aligned directly behind the openings, just as we would have expected at the very beginning. It is as though the wave-like behavior has quietly disappeared, as though the particle, once free to explore multiple possibilities, has now committed to a single path, one opening or the other. And the most striking part is this: nothing about the physical setup, apart from the presence of that detector, has changed. The particles are the same, the openings are the same, the screen is the same. The only difference is that we now have information about the path, and that information seems to alter the outcome. It is a gentle but profound shift. The pattern that once reflected overlapping possibilities is replaced by a pattern that reflects definite choices. And from this, a deeper insight begins to emerge. It is not just interaction that matters, it is information. The availability of information about what happened. When the path remains unknown, when there is no record of which opening the particle passed through, the possibilities remain open and the wave-like pattern appears. But when the path becomes knowable, even if no one actually looks at the data, the possibilities narrow and the particle behaves as though it has chosen a single route. It is as if the universe itself responds to the presence of information. Not to awareness, not to observation in the human sense, but to the existence of a record, a trace, a way of distinguishing one possibility from another. This leads to a quiet and somewhat surprising idea, that the act of asking a question can shape the answer, not metaphorically, but physically. The moment we set up a way to know which path the particle takes, the behavior of the system changes. The gentle overlap of possibilities is replaced by a single definite outcome, and this does not require anyone to actually read the result. The detector could record the information and store it quietly, unseen, and the effect would still occur. It is the possibility of knowing that matters, the presence of distinguishable paths. Now, to soften this idea, imagine a simple scenario. You're walking through a quiet garden with two paths that diverge around a small grove of trees. If no one is watching and no marks are left behind, it becomes difficult to say which path you took. From the outside, both possibilities remain open, but if you leave footprints in the soil, or if someone places a small marker along one path, then suddenly the ambiguity disappears. The path becomes known, or at least knowable, and with that knowledge the story becomes fixed. In the quantum world, something similar seems to happen. When there is no trace of the path, no information that distinguishes one possibility from another, the system behaves in a way that reflects multiple possibilities at once. But when a trace exists, when the path can be known, even in principle, the system behaves as though only one possibility is real. This leads to a beautifully simple yet deeply profound insight. Information shapes reality, or perhaps more gently, the availability of information influences how reality unfolds. It is not that the particle decides to behave differently because it is being watched. It is that the structure of the system changes when information becomes available. The possibilities are no longer free to overlap in the same way. They become distinct, and once they are distinct, the wave-like pattern cannot form. Because that pattern depends on the ability of possibilities to blend, to interfere, to remain indistinguishable. When distinction enters the picture, the blending fades, and with it, the pattern changes. There is something quietly poetic about this. A world where not just matter and energy, but information itself plays a role in shaping what becomes real. A world where the questions we ask, through the way we interact with a system, can influence the answers we receive. And yet, even here, we must be careful not to overstate the mystery. The particle is not aware. It does not feel watched. It does not respond to curiosity in any human sense. What changes is the structure of the system, the relationships between its parts, the presence or absence of information that distinguishes one possibility from another. And through those relationships, the behavior we observe emerges. Still, the effect remains deeply surprising, because it challenges a simple and intuitive belief that reality is fully formed, independent of how we choose to observe it. Instead, it suggests something more subtle, that the way we set up our interactions, the questions we allow the universe to answer, can influence the form that reality takes, not completely, not arbitrarily, but in ways that are quiet, consistent, and deeply woven into the fabric of the quantum world. So as you rest with this idea, let it settle gently. The moment you ask a question, reality answers differently, not loudly, not dramatically, but in a soft shift, from possibility to certainty, from overlap to distinction, from many paths to one. And as we continue, we will see how this interplay between information and reality leads to even stranger connections, connections that stretch across space itself, linking distant particles in ways that seem to defy everything we thought we understood about distance and separation. If you pause for a moment and look back at what we've seen so far, a quiet pattern begins to emerge. Light behaves like a wave when its path is unknown, and like a particle when that path becomes knowable. Possibility and information seem to be woven together, gently shaping what becomes real. And now, as we move forward, that relationship begins to stretch, not just across different paths, but across distance itself. Imagine for a moment that instead of a single particle, we create a pair. These two particles are born together in the same event, like two notes struck at the same time on a quiet instrument. From the very beginning, they share a connection, not a visible thread, not a signal passing between them, but something more subtle. Their properties are linked. To make this easier to feel, imagine a simple analogy. you have two coins. But these are not ordinary coins. They are prepared in such a way that whenever one is found to be heads, the other will always be tails. No matter where they are, no matter how far apart they have been taken. At first, this may not seem particularly strange. After all, if you prepared the coins in advance, if you already knew one was heads and the other tails, then their behaviour would be completely predictable. But in the quantum world, something different happens. Before you look at either coin, neither one has a definite state. They are not secretly heads or tails waiting to be revealed. Instead, each one exists in a soft state of possibility, similar to the spinning coin we imagined earlier. And yet, the moment you observe one of them, when it gently settles into heads or tails, the other one also settles, instantly, into the corresponding state, even if it is far away, even if it is on the other side of the world, or beyond. This is the phenomenon known as quantum entanglement. But rather than focusing on the name, it is more helpful to feel the structure of it. Two systems, once connected, continue to share a single story. Not two separate narratives, but one. A story that unfolds in a coordinated way, no matter how far apart the characters become. To make this a little more tangible, imagine two dancers who begin their movement together, perfectly synchronized. Then slowly, they drift apart, moving to opposite ends of a large stage. From a distance, they appear separate, and yet, if one of them turns, the other turns in a way that complements it, as though they are still following the same choreography. Not because they are communicating in real time, but because their movements are part of a shared structure that was established from the beginning. In the quantum world, entangled particles behave in a way that echoes this idea. Their properties are not independent, they are defined together, so when one becomes definite, the other does as well. And what makes this especially striking is the immediacy of the correlation. There is no delay, no signal travelling between them that we can detect. The moment one is measured, the state of the other is known. Now, it is important to be careful here. This does not mean that information is being sent faster than light in the usual sense. There's no usable message being transmitted, no way to control the outcome on one side in order to influence the other. And yet, the correlation remains. A quiet, persistent connection that does not fade with distance. This is what unsettled many physicists, including Albert Einstein, who famously referred to this behaviour as spooky action at a distance. It was not that he denied the experimental results. It was that the implications seemed to challenge something very deep in our understanding of the world. We're used to the idea that objects are influenced by their immediate surroundings. That causes propagate through space gradually, step by step. But here, the connection appears to bypass that gradual process. It feels instantaneous, and that raises a quiet but powerful question. Are these particles truly separate, or are they, in some sense, still part of a single system, even when they are far apart? From our everyday perspective, separation feels absolute. Two objects in different places are independent, but entanglement suggests that, at a deeper level, this independence may not be complete, that there are connections woven into the fabric of reality that do not rely on distance in the way we expect. To sit with this idea, imagine writing a story across 2 pages of a book. On one page, you write the beginning of a sentence. On the other page, you write the ending. Even if the pages are separated, even if they are placed far apart, they still form a single sentence, a single meaning. In the same way, entangled particles seem to form a single, shared description. And when we observe one part of that description, the rest becomes clear. Not because something travels between them in that moment, but because they were never fully independent to begin with. There is something quietly profound in this. It suggests that the boundaries we perceive, between here and there, between one object and another, may not be as fundamental as they appear, that beneath those boundaries lies a deeper level of connection, a level where relationships matter more than positions, where the story is not written in isolated pieces but as a whole. And yet, even with this perspective, the mystery does not disappear, it simply changes shape. Because while we can describe these correlations, while we can predict them with great accuracy, we are still left with the question of how to understand them. What does it mean for two distant systems to share a single state? What does it mean for reality to be structured in this way? There is no simple answer, but there is a quiet invitation to loosen our attachment to the idea that everything must behave in a familiar, classical way, to allow for the possibility that the universe is more interconnected than it appears. And as we continue, we will see how this tension between our classical expectations and the strange behaviour of the quantum world led to one of the most important turning points in physics, a moment where philosophy met experiment, and the universe responded in a way that no one could ignore. There are moments in the history of science when a discovery feels less like a triumph and more like a quiet disturbance, not because it is wrong, but because it does not sit comfortably with everything else we believe to be true. Quantum entanglement was one those moments. As we just explored, two particles can be prepared in such a way that their properties remain deeply connected even when they are far apart. The moment one settles into a definite state, the other does as well, instantly and without any visible signal passing between them. The experiments are clear. The predictions match the results. And yet, for many physicists, including Albert Einstein, something about this felt incomplete, not incorrect, but unfinished. Einstein had spent much of his life uncovering the structure of the universe at its deepest levels. He had shown that space and time are woven together, that gravity is not a force pulling objects, but a gentle curvature in the fabric of space-time. His work revealed a universe that was subtle, elegant, and above all consistent. And within that consistency, there were two quiet principles he held very close. They are simple ideas, but they shape the way we understand reality. The first is the idea of locality. Locality means that objects are influenced directly only by what is near them. If something happens here, its effects spread outward gradually, like ripples on water. Nothing jumps instantly from one place to another without passing through the space in between. This idea aligns with one of the most important features of relativity, that nothing can travel faster than the speed of light. Information, influence, and cause all move step by step, never skipping across space in a single leap. The second idea is realism. Realism suggests that physical properties exist whether or not we observe them. Particle has a position, a direction, a set of characteristics that are already defined even before we measure them. Observation reveals those properties. It does not create them. These two ideas, locality and realism, feel deeply natural. They match our everyday experience. They provide a stable foundation for understanding how the world works. But entanglement seems to challenge both. If two particles can instantly reflect each other's state across vast distances, then locality appears to be violated. Something about their connection does not respect the usual limits of space. And if those particles do not have definite properties until they are observed, then realism begins to soften as well. The idea that things are fully defined before measurement becomes less certain. Einstein found this deeply troubling, not because he rejected the experimental results, but because he believed that the theory must be missing something. He, along with two colleagues, proposed a thought experiment, often referred to as the EPR paradox, named after the first letters of their surnames. Rather than diving into the details, we can feel the essence of it. They imagined a situation very much like the one we described earlier. Two particles connected in such a way that measuring one would immediately reveal something about the other. And from this, they argued that the particles must already possess definite properties before measurement. Otherwise, the act of measuring one would somehow have to influence the other instantly across space. And that to Einstein felt unacceptable. So he suggested an alternative. Perhaps the particles carry hidden information, details about their state that we simply cannot see yet, hidden instructions that determine the outcome of any measurement in advance. In this view, the world would remain local and realistic. Everything would still be defined ahead of time. We would simply be unaware of the deeper structure guiding those outcomes. It is a comforting idea, one that restores the sense of order, of predictability, of a universe that behaves in a consistent and understandable way. And for a time, it remained a possibility, a quiet hope that beneath the strange behavior of quantum mechanics, there might be a more complete description waiting to be discovered. But as the years passed, this hope was tested, carefully, thoughtfully through experiments designed to explore exactly this question. Could the universe be both local and realistic in the way Einstein imagined? Or does quantum mechanics reveal something more subtle, something that resists that familiar framework? These experiments did not rely on complex equations alone. They relied on patterns, on correlations, on the careful comparison of measurements made on entangled particles under different conditions, and the results, when they came, were both clear and deeply surprising. They suggested that the combination of locality and realism, taken together, cannot fully explain what we observe, that at least one of these intuitive principles must be set aside, not discarded entirely but softened, reconsidered. This does not mean that signals are freely travelling faster than light, or that causality is broken in a dramatic way. But it does mean that the structure of reality may not align perfectly with our expectations, that the connections between distant parts of the universe may be more subtle than simple cause and effect, and that the properties of a system may not be fully defined until they are part of an interaction. There is a quiet humility in this realization, a recognition that even the most brilliant minds can encounter ideas that stretch beyond the limits of intuition. Einstein himself did not fully accept this outcome. He remained convinced that a deeper theory would eventually restore the clarity he sought. And perhaps, in some way, that search continues. But the experiments have spoken, not loudly, but with steady consistency. And what they suggest is that the universe is not bound entirely by the rules we once thought were absolute. Instead, it invites us to consider a more nuanced picture, one where locality and realism are not always both present in the way we expect, where connections can exist without direct signals, where properties may emerge through interaction rather than existing fully formed in advance. As you sit with this idea, there's no need to resolve it completely. It is enough to notice the shift, the gentle loosening of assumptions that once felt solid, the opening of a space where new ways of understanding can begin to take shape. And in that space, we are led naturally to the next step, a moment in physics where this philosophical tension was transformed into something measurable, where the question was no longer just what might be true, but what can we test? And in that moment, the universe offered an answer that continues to echo quietly through everything we've come to understand about reality. There are times when a question lingers for years, even decades, quietly waiting for the right moment to be asked in a new way. The tension we just explored, the unease between quantum behavior and our classical expectations, was one of those questions. Einstein and his colleagues had suggested that perhaps something was missing, that beneath the strange patterns of quantum mechanics, there might be a deeper layer of hidden information, quietly determining the outcomes of every measurement. It was a hopeful idea, one that preserved the comforting sense that reality is both local and well-defined, that things have definite properties and that influence travels step by step through space. For a time, this idea remained a possibility, but then a physicist named John Bell approached the problem from a different angle. Instead of debating the philosophy directly, he asked a more concrete question. If hidden information truly exists, if particles carry definite properties that we simply cannot see, then there should be a way to test this. There should be patterns in the measurements that reflect that hidden structure. And if those patterns do not appear, then the idea of hidden variables, at least in its simplest form, cannot be correct. Bell's insight was subtle, but powerful. He derived a kind of boundary, a limit on how strongly two distant particles could be correlated if their behaviour were guided only by local hidden information. Rather than thinking of it in mathematical terms, we can imagine it more gently. Picture two distant observers, each measuring one of a pair of entangled particles. They perform their measurements in different ways, choosing between a few possible settings, like adjusting the angle of a filter or the orientation of a detector. If the particles already carry definite instructions, if their outcomes are predetermined, then the correlations between their results can only be so strong. There is a natural ceiling, a limit that cannot be exceeded without some form of direct influence between the particles. This limit is what Bell identified, a quiet boundary between what is possible under classical assumptions and what would require something more. Now, the next step was to perform the experiment, to create entangled particles, send them far apart and measure their properties under carefully controlled conditions, to compare the results and see whether they stayed within that boundary. If they did, then Einstein's intuition might still hold. If they did not, then the universe would be telling us something unexpected. The experiments were carried out, not just once but many times by different groups, using increasingly precise equipment, and the results were clear. The correlations between the particles exceeded the classical limit, again and again, in ways that could not be explained by hidden instructions carried from the start. It was as though the particles were more deeply connected than any classical picture would allow, not by signals travelling back and forth, but by a shared structure that did not depend on distance in the usual way. This does not mean that information is being sent faster than light in a way we could use. There is no way to control the outcome on one side and send a message to the other, but the correlation itself, the pattern in the results, goes beyond what local realism can explain. And so, quietly, the universe seemed to offer an answer, not in words, but in behaviour. If we hold on to the idea that influences do not travel faster than light, then we must soften the idea that properties are fully defined before measurement. Or, if we insist that properties are always definite, then we must accept that some form of connection exists that does not respect the usual limits of space. Either way, something has to give. The two comforting principles, locality and realism, cannot both remain exactly as we once imagined. This realization did not arrive with drama. There was no single moment where everything changed. Instead, it unfolded gradually through repeated experiments, each one reinforcing the same quiet conclusion. And over time, it became clear that the quantum description of reality, strange as it is, captures something essential about how the world works. There's a certain stillness in this understanding, a sense that the universe is not broken, not chaotic, but simply different from what we expected. More interconnected, more subtle, less bound by the simple, linear picture of cause and effect that feels so natural to us. To sit with this idea, imagine once again that story written across two distant pages. If you insist that each page must be completely independent, you may struggle to explain how they form a single sentence. But if you allow for a deeper connection, a structure that spans both pages, then the coherence of the sentence becomes clear. In the same way, entangled particles seem to share a structure that is not confined to a single location. And when we measure them, we're not revealing independent properties, but participating in a joint description that spans both. There is something quietly beautiful in this, a suggestion that the universe is not divided into isolated pieces, but woven together in ways that are not always visible at first glance. And yet this beauty comes with a gentle challenge. It asks us to loosen our grip on certain assumptions, to accept that the world may not be fully captured by the categories we find most intuitive, to allow for the possibility that reality, at its deepest level, is not entirely local, not entirely predetermined, but something more fluid, more relational. And as we continue, this idea of information, of what is known, what is recorded, what is distinguishable, will begin to take on an even more intriguing role. Because it turns out that not only can information shape the present, it can also influence how we understand the past, not by changing what has already happened, but by changing the story we are able to tell about it. There is a quiet assumption we often carry with us that the past is fixed. What has happened has happened. A path was taken, an event occurred, a choice was made. And no matter what we learn later, that past remains unchanged, steady and unmoving, like ink dried on a page. But in the quantum world, even this gentle certainty begins to soften, not in a dramatic way, not in a way that rewrites history or sends anything backward through time, but in a more subtle sense, a shift in how the past can be described. To explore this, we return once more to the experiment with two openings. We have seen that when we do not know which path a particle takes, the pattern on the screen reflects many possibilities overlapping, soft bands of light and shadow, like ripples meeting on water. And we have also seen that when we place a detector to find out which path the particle takes, that delicate pattern disappears. The possibilities separate, and the result becomes simple and definite. Knowing the path changes the outcome. Now, imagine something slightly more intricate. We still allow the particle to pass through the two openings, and we still include a way of recording which path it takes. The information is captured, stored somewhere in the system quietly and without disturbance. At this point, we would expect the pattern on the screen to be simple. Two clear regions reflecting definite paths, and indeed it is. But now we introduce one more gentle step. After the particle has passed through the openings, after the path information has been recorded, we perform an additional process. We erase that information, not by travelling back in time, not by undoing the particle's journey, but by removing the possibility of knowing which path was taken. The record is no longer distinguishable. The information, in a practical sense, is gone. And here is where something quietly astonishing occurs. When we look at the pattern on the screen, not all at once but carefully by grouping the results according to how the information was handled, we find that the wave-like pattern reappears. The interference returns, as though the particle had once again behaved like a spread of possibilities, even though earlier in the process we had allowed the path to be known. Now, this does not mean that the past has changed. The particles still pass through the system in exactly the same way, but the way we're able to describe that past, the story we can tell about it, depends on whether the information remains available or not. If the path information is preserved, the particle behaves as though it took one definite route. If that information is erased, the particle behaves as though it explored multiple paths. It is not the physical journey that changes, it is the structure of the information, and how that structure shapes the patterns we observe. To feel this more gently, imagine reading a mystery novel. At the beginning, you are presented with several possibilities. Different characters, different motives, different paths the story could take. The narrative is open, uncertain, filled with overlapping threads. As you continue, reading clues appear, information accumulates, certain possibilities become more likely, others fade away. And then, at some point, the mystery is resolved, a single explanation is revealed, and the story becomes definite. But now imagine that the final chapter is removed. The explanation is erased. Suddenly the story changes, not in what physically happened on the pages, but in how you understand it. The uncertainty returns. Multiple interpretations become possible again. In a similar way, the quantum eraser experiment shows that the presence or absence of information shapes how we interpret the sequence of events, not by changing the past itself, but by changing the framework through which the past is understood. This is a subtle distinction, but an important one. Nothing travels backward in time. No signal is sent into the past to alter what has already occurred. Instead, the structure of the present, the availability of information, affects how the outcomes are grouped, how the patterns are revealed, and how the story of the experiment unfolds. It is as though the past is not a single, fixed narrative, but a collection of possibilities that become more or less defined depending on the information we hold. And this leads to a gentle, almost dreamlike insight. That time, at least at the quantum level, may not be as strictly linear as it appears, not broken, not reversed, but more flexible in how events are connected and described. The present does not rewrite the past, but it does influence how the past is organized into meaning. And meaning, in this context, is what allows us to see patterns, to distinguish between possibilities, to say what really happened. There is something quietly poetic about this. A world where information is not just a passive record, but an active ingredient in shaping reality, where the act of preserving or erasing information can influence the patterns that emerge even after the events themselves have already taken place. It invites us to reconsider the relationship between past and present, not as a rigid sequence where each moment is locked into place, but as a more fluid connection where meaning unfolds over time. And as you sit with this idea, there is no need to resolve it fully. It is enough to feel the softness of it, the way it gently loosens our usual sense of time, the way it suggests that reality is not just about what happens, but about how what happens is connected, recorded, and understood. And from here, a deeper question begins to emerge. If information can shape the way we describe the past, then what determines which description is the real one? Is there a single objective story? Or can different observers, with access to different information, experience different versions of reality? This is where our journey turns inward, toward a more intimate and philosophical layer, a place where observation is not just about interaction, but about perspective, and where the question of what is real becomes a little more personal. There is a quiet habit in the way we think about time. We imagine it as a steady flow, moving in one direction. The past sits behind us, fixed and unchanging. The future lies ahead, open and unknown. And the present is the thin, moving line where one becomes the other. It feels simple, comforting even. But as we just explored, the quantum world introduces a subtle shift in this picture. Not a dramatic reversal of time, not a breaking of cause and effect, but something more delicate, a soft bending in how events are connected. When we spoke about erasing information, we saw that the pattern we observe can depend on whether certain details remain available. If the path of a particle can be known, the result appears simple and definite. If that information is no longer accessible, the result reflects a blend of possibilities. And this leads us to a question that feels almost like a whisper. When, exactly, does reality decide what it has been? Not in the sense of rewriting the past, but in the sense of how the past becomes meaningful, how it takes on a definite shape in the story we can tell. To explore this gently, imagine watching a film for the first time. At the beginning, you see a series of events unfold. A character walks into a room, glances at an object, leaves without explanation. The moment feels ordinary, perhaps even unimportant. But later in the film, a new piece of information is revealed. That object was significant. The glance carried meaning. Suddenly the earlier scene changes, not in what physically happened, but in how you understand it. The past remains the same, but its meaning has shifted. The story has been reshaped by what you learned later. In the quantum world, something similar seems to occur, though in a more subtle and precise way. The outcomes we observe can depend on how information is arranged, even if that arrangement is determined after the particle has already moved through the system. This does not mean that the future is sending signals into the past. It does not mean that cause and effect are reversed. Instead, it suggests that the description of events, the way we organize and interpret what has happened, is not fully settled until the relevant information is in place. It is as though reality at this level is not a single, fixed narrative unfolding step by step, but a structure that becomes more defined as information accumulates. A story that is not completely written at the moment each event occurs, but gradually takes shape as the pieces come together. To feel this more intuitively, imagine standing in a room filled with scattered puzzle pieces. At first, the pieces seem disconnected. You can see fragments of colour, hints of shapes, but no clear picture. As you begin to assemble them, the image slowly emerges. A pattern forms. Relationships become clear, and what once felt random begins to make sense. Now, imagine that some pieces are added later. Pieces that change how the earlier fragments fit together. Again, nothing about the individual pieces has changed, but the overall picture, the meaning of the arrangement, has evolved. In a similar way, the quantum eraser experiment suggests that the patterns we observe depend not just on the sequence of events, but on the structure of information that connects them. The present does not alter the past, but it does influence how the past is organized into a coherent whole. And this brings us to a gentle but important realization. Time, as we experience it, may not capture the full structure of reality. We feel events unfolding in a straight line, one after another. But at a deeper level, the relationships between events, the way they're connected through information, may not be strictly linear. Instead, they form a kind of web, a network where past, present, and future are linked in ways that are not always visible from our everyday perspective. This does not make time meaningless. It does not remove the order we experience in daily life, but it does suggest that the deeper structure of reality is more subtle than a simple sequence of moments. It is shaped not only by when things happen, but by how they are connected, how information flows between them, and how that information is used to form patterns. There is a quiet elegance in this idea, a sense that reality is not just a chain of events, but a tapestry of relationships. And within that tapestry, the present plays a special role. It is the point where information becomes available, where connections are revealed, where the structure of the past becomes clear. In this sense, the present does not change what has happened, but it does help define what that happening means. And meaning, as we've seen, is closely tied to what we observe, to the patterns we can detect, to the distinctions we're able to make. As you rest with this thought, there is no need to force it into something rigid. It is enough to feel the softness of it, the way it gently expands our sense of time, the way it invites us to see reality not as a fixed sequence, but as something more fluid, more interconnected. A story that unfolds not only forward, but also through the relationships between its parts. And from here, a new question begins to emerge. If the structure of reality depends on information, and if that information shapes how events are understood, then what happens when different observers have access to different information? Do they share the same reality? Or can reality itself take on different forms depending on perspective? It is a quiet question, but one that leads us into one of the most intimate and thought-provoking ideas in all of quantum physics. There is a quiet assumption we carry without noticing. That reality is the same for everyone. If two people stand in the same room looking at the same object, we expect them to agree on what they see. The colour, the position, the shape. These things feel stable, shared, objective. It is a comforting idea, a sense that the world exists in a single, consistent way, independent of who is observing it. But as we move deeper into the quantum world, even this assumption begins to soften. Not suddenly, not dramatically, but in a way that invites a more careful look. To explore this, imagine a simple situation. There is a small, sealed room. Inside the room, an experiment is taking place. A single quantum system, perhaps a tiny particle, is prepared in a state of possibility, not yet settled into a definite outcome. Inside the room, there is an observer. This observer performs a measurement. They interact with the system, and in doing so, they obtain a result. For them, the uncertainty resolves. The system becomes definite. A single outcome appears. From their perspective, reality has settled. Now, outside the room, there is another observer. This second observer does not yet know the result of the experiment. They have not interacted with the system, nor with the observer inside. From their point of view, the entire room, the particle, the measuring device, and even the observer inside can still be described as a combined system of possibilities, a soft, unresolved state. So we have two perspectives. Inside the room, the outcome is definite. Outside the room, the outcome is still a range of possibilities. Both descriptions are consistent within their own frames of reference. And this is where the quiet tension appears. Can both of these realities be valid at the same time? This thought experiment, often associated with Eugene Wigner, does not provide a simple answer. Instead, it gently highlights a question that has been present all along. When exactly does reality become definite? Is it when the first observer makes a measurement, or only when the result becomes known to others? Is there a single objective moment of collapse, or is definiteness relative to the observer? To feel this more intuitively, imagine two people watching the same story unfold, but with different levels of information. One person has seen the ending. They know how everything resolves. For them, the story is complete, settled, fully understood. The other person is still in the middle. The outcome is uncertain. Multiple possibilities remain open. They are experiencing the same narrative, but in different states of knowledge. And in a subtle way, their realities are different. Not because the events themselves have changed, but because the information available to each observer shapes how those events are described. In the quantum version of this situation, the difference is more profound. The outside observer does not simply lack information. They describe the system itself as being in a different state, a state that still contains multiple possibilities, while the inside observer describes a single, definite outcome. Both descriptions are valid within the framework of quantum mechanics, and yet they do not align in a simple classical way. This suggests something quietly remarkable. That reality, at least at this level, may not be fully absolute. It may depend, in part, on the perspective from which it is described. not in a subjective sense where anything can be anything, but in a structured, consistent way where different observers can have different, yet equally valid descriptions of the same system. This does not mean that the world is chaotic or inconsistent. There are still rules, still patterns, still a deep coherence that holds everything together. But it does mean that the idea of a single, observer-independent reality becomes more subtle, more nuanced. To sit with this idea, imagine standing on opposite sides of a mountain. One side is bathed in sunlight, the other rests in shadow. From one perspective, the mountain is bright and warm, from the other it is cool and dim, both. Descriptions are true, neither captures the whole. Only when the perspectives are brought together does a fuller picture emerge. In a similar way, quantum mechanics allows for different perspectives to coexist, each reflecting a part of the system structure. And the act of sharing information, of bringing those perspectives together, plays a role in aligning those descriptions. When the outside observer opens the room and learns the result, the two perspectives converge. The uncertainty resolves. A single, shared reality emerges. But before that moment, the system can be described in different ways, depending on who is observing and what they know. There is something deeply thought-provoking in this. It suggests that reality is not just a collection of objects and events, but also a web of relationships between observers and systems. That what is real is not only about what exists, but about how it is connected, measured and described. And as you rest with this idea, there is no need to force it into something fixed. It is enough to feel the openness of it. The way it gently challenges the assumption that there is always a single, fully defined version of events, independent of perspective. The way it invites us to consider that reality may be richer, more layered, more relational than we once imagined. And from here, a new question naturally begins to form. If reality can depend on perspective, if different observers can hold different yet valid descriptions, then where exactly does reality finally take shape? At what point do these perspectives come together into something definite? Is there a boundary, a place where the soft possibilities of the quantum world give way to the solid certainty of the classical one? Or is that boundary itself more fluid than we expect? There is a quiet place between two ways of seeing the world. On one side, there is the quantum picture we have been slowly uncovering, a world of possibilities, of overlapping states, of outcomes that are not fully defined until interaction brings them into focus. On the other side, there is the world we experience every day, solid, stable, dependable, a place where objects have clear positions, where events unfold in a predictable way, and where reality feels settled. Both of these pictures are true, and yet they feel very different. So a natural question begins to emerge. Where is the boundary? At what point does the soft, fluid world of quantum possibilities give way to the firm, definite world we experience? Is there a specific scale, a particular size where this transition occurs? Or is the shift more gradual, more subtle, more difficult to locate? To explore this, imagine a single particle, isolated as much as possible from its surroundings. In this quiet isolation, it can maintain its delicate state of possibility. It is not fully committed to a single outcome. It behaves in a way that reflects multiple potential states at once. Now begin to introduce interactions. A faint glow of light touches it, a gentle vibration from the surrounding environment, a subtle exchange of energy with nearby particles. Each interaction leaves a trace. Each one carries a small amount of information about the system into the wider world. And with each trace, something begins to change. The delicate balance of possibility starts to fade. Not suddenly, not all at once, but gradually. Like a mist thinning in the morning light, the system becomes more and more entangled with its surroundings. Its state is no longer independent, no longer isolated. Instead, it becomes part of a larger, more complex network of interactions. And as this network grows, the ability to maintain a clear superposition, those overlapping possibilities, begins to disappear. This process is often described using technical language, but we can feel it more simply. It is the process by which the quantum world blends into the classical one, a gradual loss of ambiguity, a quiet settling into definiteness. To make this more tangible, imagine writing with a pencil on a blank sheet of paper. At first, the surface is smooth, untouched, full of potential. You could draw anything. The possibilities are open. But the moment you begin to write, marks appear. Lines form. The page becomes more defined. And once those marks are made, they cannot easily be undone. The page has taken on a specific shape. In a similar way, interactions leave marks on a quantum system. Not visible marks, but informational ones. Records of what has happened, carried into the environment. And as those records accumulate, the system becomes more and more constrained. The possibilities narrow. The outcome becomes fixed. This process does not require a conscious observer. It does not depend on someone watching or recording the result. It happens naturally, continuously, as systems interact with their surroundings, and it helps explain why we do not see quantum superpositions in everyday life. Why a cup is not both on the table and not on the table. Why a person is not in two places at once. Because at that scale, interactions are constant. The environment is always present, always exchanging information, always shaping the system into a definite state. The delicate balance required for superposition is quickly lost, and what remains is the stable, classical world we are familiar with. But even with this understanding, the question does not disappear entirely, because while this process explains how possibilities become less visible, it does not fully explain why only one outcome is experienced. Why, among all the possibilities, we observe a single result. Why the world appears as one consistent story rather than many overlapping ones. This brings us back gently to the deeper mystery, the question of where reality actually forms. Is it in the interaction itself? In the accumulation of information? In the moment, when a system becomes entangled with its environment? Or is it something else, something not yet fully understood? Some interpretations suggest that the process is complete once the system interacts with the environment, that the outcome becomes effectively fixed at that point, even if we do not yet know what it is. Others suggest that all possibility continue to exist, but that our experience is limited to a single branch, a single thread within a much larger tapestry. And still others propose that the transition is not a fundamental change, but an emergent one, a result of complexity, of scale, of the way many small interactions combine to produce a stable outcome. There is no single answer that resolves all of these perspectives, but there is a quiet insight that begins to take shape, that reality may not form at a single point, that there may not be a sharp boundary between the quantum and the classical. Instead, there may be a continuum, a gradual unfolding, a process in which possibilities become less and less visible, more and more constrained, until they appear as a single definite outcome, like a photograph slowly coming into focus. At first, everything is blurred. Many details overlap, indistinct and uncertain. Then, as the image sharpens, the outlines become clear. The scene resolves into a single, coherent picture, but there was no single instant where the image changed from unclear to clear. It happened gradually through a continuous adjustment. In the same way, the formation of reality may not be a single event, but a process a gentle narrowing of possibilities shaped by interaction, by information, by the connections between systems. And as you rest with this idea, there is no need to locate a precise boundary. It may not exist in the way we expect. It may be that reality is always forming, always settling, always moving from possibility toward definiteness, guided by the quiet interplay of interaction and information. And from this perspective, a new kind of question begins to emerge. If observation and interaction can shape reality, if they can narrow possibilities and influence outcomes, then what happens when observation is not just a passive process, but something continuous? What happens when a system is watched, not once, but over and over again? Does it continue to evolve as usual? Or does something else begin to occur? Something even more subtle, and perhaps even more surprising. There's a familiar feeling we all know. You place a pot of water on the stove, waiting for it to boil. You glance at it once, then again, and somehow it feels as though the water takes longer to change. Of course, we know that in everyday life, watching the pot does not truly slow the boiling. The process continues at its own steady pace, whether we are paying attention or not. And yet, in the quantum world, something surprisingly similar begins to take shape, not as an illusion, but as a real effect. To explore this gently, imagine once again a tiny system, a single quantum state, holding the possibility of change. Left alone, this system evolves naturally. It moves from one state toward another, following a quiet, continuous path. Not in the rigid, predictable way of classical motion, but in a smooth unfolding of possibilities. Over time, the likelihood of finding it in a new state increases. Change is part of its nature. Now, imagine that instead of leaving the system alone, we begin to observe it. Not once, but repeatedly. At very short intervals, we gently interact with the system, asking the same simple question each time. Are you still in your original state? Each interaction is small, subtle, a brief contact that gathers information and leaves a trace, and something curious begins to happen. With each observation, the system is gently nudged back toward its original condition. The unfolding of possibilities is interrupted. The transition toward a new state slows, and with frequent enough observation, it can nearly stop altogether. It is as though the act of checking, of asking the question again and again, prevents the system from changing. This phenomenon is known as the Quantum Zeno effect, but rather than focusing on the name, it is more helpful to feel the shape of it, a system that would naturally evolve over time, held in place by repeated interaction. Not frozen in a rigid sense, but gently restrained, its motion slowed by the constant renewal of its current state. To make this more intuitive, imagine a delicate balance, a small object resting at the top of a gentle slope. Left undisturbed, it would slowly roll downward, moving into a new position. But if you return again and again, placing your hand lightly against it, steadying it each time it begins to move, the motion is interrupted. The object remains near its starting point, not because the slope has disappeared, but because the process of movement is repeatedly reset. In the quantum world, observation plays a role similar to that gentle touch. Each measurement brings the system back into a definite state, and if those measurements happen frequently enough, the system does not have time to drift far from where it began. Its evolution is slowed, its change is suppressed. There is something quietly remarkable in this, because it suggests that observation is not only a way of revealing reality, but also a way of influencing how that reality unfolds over time, not by forcing a specific outcome, but by shaping the conditions under which change can occur. Now, it is important to keep this idea soft. We're not saying that observation creates control in the everyday sense. We cannot simply watch something and stop it from changing at will. The effect depends on precise conditions, on carefully timed interactions, on systems that are delicate enough for this influence to be visible, and yet the principle remains that the act of observation, of interaction, can influence not just what is observed, but how it evolves. To feel this more gently, imagine reading a sentence slowly, one word at a time. If you pause after each word, reflecting on it, the flow of the sentence is interrupted. The meaning unfolds more slowly, the progression held back by your attention. But if you read the sentence smoothly without interruption, the meaning emerges naturally, flowing from beginning to end. In a similar way, the quantum system's evolution can be slowed by repeated pauses, moments of interaction that prevent the full unfolding of possibilities. And this leads to a subtle but profound insight. That time at this level is not just a passive backdrop. It is something that can be shaped, gently, by the structure of interaction. Not stopped entirely, but influenced, guided, softened. There is a quiet elegance in this idea, a sense that the flow of change is not completely independent, but connected to the way systems interact, to the way information is gathered and recorded. And as you rest with this thought, you might notice how it connects with everything we have explored so far. Observation shapes reality, information defines outcomes, and now observation also shapes how reality changes over time. It is as though these ideas are weaving together into a single coherent picture, a picture where reality is not fixed, not entirely independent, but responsive to interaction in subtle and consistent ways. And from here, a new curiosity begins to emerge. If observation can slow change, if interaction can influence evolution, then what happens when we take this idea even further? What happens when we design a situation where information is gained without direct interaction, where we learn something about a system without touching it in the usual sense? It sounds almost impossible, and yet in the quantum world even this becomes possible. There is a quiet assumption that feels almost impossible to question, that to know something, you must, in some way, interact with it. You must touch it, or see it, or allow some form of energy to pass between you and the thing you are observing. A kind of gentle contact, however small, that leaves a trace. In everyday life, this feels undeniably true. If you want to know whether a cup is warm, you place your hand near it. If you want to know whether a light is on, you look toward it. Even the act of seeing involves particles of light reaching your eyes, carrying information from the world to you. Knowledge, it seems, requires interaction. And yet, in the quantum world, even this assumption begins to soften. Not in a dramatic way, but in a way that opens a small and surprising possibility. That under certain conditions, it is possible to learn something about a system, without interacting with it directly. To explore this, imagine a simple scenario. You're given a collection of objects, identical in appearance. Some of them are harmless, but one of them is special in a delicate way. If it is disturbed, if anything interacts with it, it will immediately change state. For the sake of imagination, you might think of it as a very sensitive device, one that reacts instantly to the slightest contact. Now, your task is to determine which object is the sensitive one, but there is a challenge. If you test it directly, if you touch it, you risk triggering the very response you're trying to avoid. So the question becomes, can you identify the special object without interacting with it in the usual way? At first, this feels impossible, and yet, through a clever arrangement, something unexpected becomes possible. To feel this more gently, Imagine once again a system with two possible paths. A particle of light enters the system and can travel along either path, much like in the earlier experiment with two openings, but now one of those paths may be blocked by the sensitive object. If the object is present, the path is unavailable. If the object is absent, both paths remain open. Now, here is the subtle part. Even if the particle does not take the blocked path, the mere presence of that path, whether it is open or closed, affects how the possibilities combine. If both paths are open, the particle behaves like a wave of possibilities, and a familiar pattern of interference can form. If one path is blocked, that pattern changes, not because the particle physically travelled along the blocked path, but because the structure of possibilities has been altered, and by carefully observing the pattern that emerges, we can infer whether the path was open or closed. In other words, we can detect the presence of the object, without the particle ever interacting with it directly. It is as though the absence of interaction itself carries information, a quiet signal, not from what happened, but from what could have happened but did not. To make this more intuitive, imagine walking into a room with two doors. One door leads to a quiet hallway, the other leads to a room that triggers an alarm if you enter. You want to know which door leads to the alarm, but you do not want to set it off. So instead of walking through the doors, you listen. You observe how the air moves, how the light shifts, how subtle patterns in the room change depending on whether the path is open or blocked. From those patterns, you begin to infer the structure of the space. You learn about the presence of the alarm without ever triggering it. In the quantum world, something similar happens. The system as a whole, the arrangement of possibilities, contains information about the presence or absence of certain paths. And by observing how those possibilities combine, we can extract that information even when no direct interaction occurs. This is often described as interaction-free measurement, but rather than focusing on the name, it is more helpful to feel the idea. That information can arise not only from what happens, but from what is prevented from happening, that the structure of possibilities carries meaning even when certain paths are never taken. There is something quietly profound in this, because it suggests that reality is not built solely from events, from interactions that occur. It is also shaped by constraints, by the boundaries of what could occur, by the presence or absence of possibilities. A world where even non-events, even paths not taken, can leave a trace in the patterns we observe. And this connects beautifully with everything we've explored so far. The idea that possibilities matter, that information shapes outcomes, that observation influences not only what is revealed, but how systems behave. Here, we see that even the absence of interaction can become a source of knowledge, a way of learning about the world without disturbing it in the usual sense. As you rest with this idea, it may feel almost like a gentle paradox, knowing without touching, learning from what does not happen. A reminder that at the quantum level, the boundaries between presence and absence, between action and inaction, are more fluid than we might expect. And from here, our journey begins to widen once more. We've explored how information shapes reality, how connections stretch across space, how time itself becomes more subtle, how observation can influence change. Now we begin to look outward, toward the larger structures in the universe, toward places where gravity becomes so intense that even light cannot escape, and where the question of information, of what is preserved, what is lost, and what remains, takes on an even deeper significance. There is a quiet principle that runs through much of modern physics. That information is never truly lost. Not in the ordinary sense of forgetting, where a detail slips from memory, but in a deeper sense, that the complete description of a system, the full set of relationships that define it, cannot simply vanish from the universe. It may become difficult to access. It may spread out, become tangled, or hidden within complexity. But in principle, it remains. This idea is woven into both classical physics and quantum theory. It is reflected in the way systems evolve, in the way patterns can be traced backward, in the expectation that if we knew enough, we could reconstruct what came before. There is a comforting continuity in this, a sense that the universe keeps a record even if we cannot always read it. But now, imagine a place where this principle is put under extreme pressure, a place where gravity becomes so strong that it reshapes space and time themselves, a place where even light cannot escape. These are what we call black holes, not as objects in the usual sense, but as regions of space where the pull of gravity becomes so intense that everything within a certain boundary is drawn inward. That boundary is often described as a point of no return. Once something crosses it, it cannot come back, not even light. Now imagine that information falls into such a region, a particle carrying with it a set of properties, a pattern of relationships, a small piece of the universe's ongoing story. It crosses the boundary, it disappears from view. From the outside it seems to be gone, and this is where the quiet tension begins. If information is truly never lost, then where did it go? Is it still there, hidden within the black hole, or has it somehow been erased? For a time, it was thought that black holes might indeed destroy information, that anything falling into them would be lost forever, leaving behind only a simple description of the black hole itself, its mass, its charge, its rotation, all the fine details gone. But this idea created a deep conflict, because quantum theory, in its most fundamental form, does not allow for information to be destroyed in this way. The evolution of a system, according to the theory, preserves the underlying information, even if it becomes difficult to track. So we are left with a paradox. Two powerful frameworks, quantum mechanics and the theory of gravity, seem to be telling us different stories. One says that information must be preserved. The other suggests that it can disappear, and for many years this tension remained unresolved. Then something unexpected was proposed. A physicist named Stephen Hawking suggested that black holes are not entirely silent, that they are not perfectly closed. Instead, they emit a faint form of radiation, a gentle release of energy that slowly carries information away. This radiation is incredibly subtle, so faint that it is almost impossible to detect directly. But over long periods of time it causes the black hole to lose energy, and eventually to fade. And with that fading, a new possibility emerges, that the information which seemed to be lost is not destroyed, but encoded in a highly complex way within this radiation, not returned in a simple, readable form, but preserved, in principle, within the patterns of what is emitted. To feel this more gently, imagine burning a book. At first glance, the information seems to be gone. The pages are reduced to ash, the words no longer visible. But if you could, in theory, track every particle of smoke, every fragment of heat, every tiny motion created by the burning process, you might be able to reconstruct the original text. Not easily, not practically, but in principle, the information is still there, dispersed into the environment. In a similar way, the information that falls into a black hole may not vanish. It may be spread out, encoded in ways that are extraordinarily difficult to decipher, but still present in the fabric of the universe. This idea has led to new ways of thinking about space, time, and information. Suggestions that the surface of a black hole, the boundary itself, may store information about everything that has fallen inside, that the universe at its deepest level may be organized not just in terms of objects and events, but in terms of information and its preservation. There is something quietly profound in this, a sense that even in the most extreme environments, even where our intuition breaks down, the universe still holds on to its story. Not always in a way we can easily read, but in a way that remains consistent with its underlying principles. And as you sit with this idea, it connects gently with everything we've explored so far. The role of information in shaping reality, the way possibilities become outcomes, the way observation, interaction, and structure all play a part in defining what we experience. Here at the edge of the universe, those same themes reappear. But on a much larger scale, information is not just a feature of small systems, it is a fundamental aspect of reality itself, something that persists, even when it seems to disappear, something that shapes the structure of the universe, from the smallest particles to the largest cosmic objects. And yet, even with these insights, the mystery does not fully resolve. We still do not have a complete theory that unites quantum mechanics and gravity. We still do not fully understand how information is preserved in these extreme conditions. But the direction is clear. That information matters, that it cannot simply be erased, that the universe, in its quiet and consistent way, keeps track of what has been. And from here, one final idea begins to emerge. If information is always preserved, if possibilities are never truly lost, then perhaps every possible outcome exists somewhere, not just as a fleeting potential, but as something real, unfolding in its own way. A possibility that leads us gently into one of the most expansive interpretations of quantum mechanics, an idea where reality does not collapse into a single outcome, but instead quietly branches. Greater, then there is a quiet idea that begins to take shape when we follow the thread of everything we have explored, that perhaps nothing is ever truly lost, not information, not possibility, only the path we happen to experience. Up until now, we have gently described how a system can exist in many possible states at once, and how interaction seems to bring one of those possibilities into focus, a soft narrowing, a settling, as though reality chooses a single outcome. But there is another way to look at this, a way that does not require any possibility to disappear. Instead of imagining that all possibilities collapse into one, imagine that they all continue, each one unfolding in its own quiet way, each one becoming real somewhere. This is often called the many worlds interpretation, but rather than focusing on the name, it is more helpful to feel the idea itself. Imagine standing at a moment of decision, a simple one. You turn left or you turn right. In your experience, only one of these happens, the other fades away, becoming something that did not occur. But in this picture, something different is suggested. Both possibilities continue, not in the same place, not in the same narrative, but in separate, gently diverging paths of reality. In one, you turn left, in another, you turn right. Each path is complete. Each one contains a version of you, continuing forward, unaware of the other. At first, this may feel overwhelming, a sense of endless branching, of reality splitting again and again with every event, every interaction, every moment where multiple outcomes are possible. But there is a way to hold this idea more softly, not as a chaotic explosion of worlds, but as a quiet unfolding of possibility. Like a tree growing, at each branch point the structure divides, but each branch remains connected to the whole, part of a larger pattern. No single branch contains the entire tree, but each one is a natural continuation of what came before. In the same way, the many possibilities present in a quantum system could be understood as different branches of a larger reality, and what we experience is just one of those branches, not because it is the only one, but because it is the one we are part of. Now, this perspective offers a different way of thinking about something we have encountered again and again, the idea of collapse. Instead of imagining that the wave of possibilities suddenly reduces to a single outcome, we can imagine that the wave continues to evolve, but becomes separated into distinct, non-overlapping branches. Each branch contains a definite outcome, and from within any one branch, it appears as though a single result has occurred. The other possibilities are still present, but no longer accessible, not gone, just elsewhere. To feel this more intuitively, imagine listening to a piece of music with multiple harmonies. All the notes exist together, forming a rich, layered sound. But if you focus your attention on a single melody line, that line becomes your experience of the music. The other harmonies are still there, contributing to the whole, but they are not what you're directly following. In a similar way, our experience of reality may be like following a single thread through a much larger fabric of possibilities. A thread that feels complete, consistent, and continuous from our perspective, even though the full structure is far more complex. Now, there is a particular extension of this idea that is often mentioned, sometimes in ways that feel unsettling. It is the suggestion that, because every possible outcome continues somewhere, there may always be a branch in which a conscious observer continues to exist, even when other branches lead to different outcomes. But it is important to approach this gently, not as something dramatic or literal, but as a reflection of the broader idea. That experience follows a path, and that path is part of a larger set of possibilities. We do not need to imagine extreme scenarios. It is enough to notice that at every moment there are many ways things could unfold, and that the path we experience is just one of them. There is something quietly comforting in this, a sense that the universe does not discard possibilities, but allows them to exist in different forms, a kind of generosity in the structure of reality, where outcomes are not eliminated but separated, where the fullness of possibility is preserved, even if our experience is limited to a single thread. And yet, this idea also carries a certain humility, because it reminds us that what we experience is not necessarily the entirety of what exists, that reality, as we know it, may be just one perspective within a much larger whole, a single story within a vast collection of stories, all unfolding together, each one consistent within its own path. As you sit with this idea, there is no need to decide whether it is true. It is one way of making sense of the patterns we observe, one way of preserving the idea that information is never lost, that possibilities are not destroyed, but transformed. And whether or not this interpretation reflects the deepest structure of reality, it offers a gentle shift in perspective, from a world where possibilities collapse into one, to a world where possibilities continue, each one finding its place. And from here, we arrive at a quiet moment of reflection. We have explored how reality can exist as possibility, how information shapes outcomes, how connections stretch across space and time, how observation influences change, and how even the structure of reality itself may be more expansive than we imagined. Now, all of these threads begin to come together, not into a final answer, but into a shape, a way of seeing, a gentle understanding of what reality might be. If you gently trace the path we've taken together, a pattern begins to emerge. At first, the world felt simple. Objects had positions, events followed one another, causes led to effects in a steady, reliable way. Reality seemed like a stage already built, where everything simply unfolded. But slowly, almost imperceptibly, that picture began to soften. We saw that at the smallest scales things are not always definite, that particles can exist as possibilities, not yet committed to a single state, that paths can overlap, that outcomes can depend on information, that observation is not just passive but part of the process. We saw that connections can stretch across distance, linking systems in ways that do not fit neatly into our classical intuition. That time itself can feel less rigid, more like a web than a straight line, that different observers can hold different yet consistent descriptions of the same situation. And now, as we sit with all of this, a quiet question begins to take shape. If we gather these ideas together, what kind of reality do they suggest? Not in terms of equations or precise definitions, but in terms of feeling, in terms of structure, in terms of the way the world might be beneath the surface we experience. One way to hold this is gently. Reality, at its deepest level, may not be made of solid objects moving along fixed paths. Instead, it may be made of possibilities, a soft field of potential outcomes, each one carrying a certain likelihood, each one part of a larger pattern. These possibilities are not random. They follow structure. They combine, reinforce, and cancel, shaping the patterns we observe. And when interaction occurs, when information is created, those possibilities narrow. They settle into definite outcomes, not because they were always fixed, but because the conditions for a definite result have been met. In this sense, reality is not entirely predetermined, nor is it completely random. It is something in between, a structured unfolding of possibility into experience. Now, if we add another layer to this picture, something else becomes clear. Information plays a central role, not just as a record of what has happened, but as an active part of how reality takes shape. When information is available, when paths can be distinguished, when outcomes can be known, the behavior of systems changes. Possibilities become separated, outcomes become definite. When information is not available, possibilities remain free to overlap. Patterns emerge that reflect that openness. So reality in this sense is closely tied to information, to what is known, to what can be known, to what is recorded in the interactions between systems. And then there is observation. Not in the sense of human awareness, but in the broader sense of interaction. The moments when systems connect, exchange information, leave traces. These moments are where possibilities meet the rest of the universe, where the soft field of potential becomes something definite, where experience arises. If you let these ideas settle together, a quiet image begins to form. Reality as a kind of flowing structure, a continuous movement from possibility to outcome, from uncertainty to definiteness, from many potential paths to a single experienced one. But even that single path is not isolated. It is part of a larger pattern, connected to other possibilities, other branches, other perspectives, all woven into a broader fabric. To feel this more intuitively, imagine standing by a river at night. The surface of the water reflects the moon, the stars, the faint glow of distant lights. The reflections shift and shimmer, never fixed, always changing. If you try to point to a single stable image, it slips away. But if you step back, you see the pattern, the movement, the coherence and the change. In a similar way, reality may not be a fixed picture. It may be a process, a continuous unfolding shaped by possibility, information, and interaction. And our experience is part of that unfolding, not separate from it, not observing from the outside, but participating in it moment by moment. There is something quietly grounding in this, a sense that the uncertainty we encounter at the smallest scales is not a flaw in the universe, but a feature, a reflection of its richness, its openness, its capacity to hold many possibilities at once before settling into form. And yet, even as these ideas come together, something remains, a softness, an incompleteness. Because for all that we have explored, for all that we have understood, there is no final picture that resolves everything. No single interpretation that answers every question. No complete theory that unites all aspects of reality into a single seamless whole. And perhaps that is part of the story. That reality at its deepest level is not something that can be fully captured in a single description. That it invites multiple perspectives, multiple ways of understanding, each one revealing a different aspect of the whole. So as you rest with this, there is no need to reach a conclusion. It is enough to feel the shape of it, a world where possibility and reality are not separate but part of a continuous flow, where information and interaction play a central role, where certainty emerges gently from uncertainty, and where the deeper we look, the more the universe reveals itself as something both precise and mysterious, something that can be studied, understood, and described, and yet always retains a quiet depth beyond our full grasp. And so we arrive at a quiet resting point, not a conclusion in the usual sense, not a final answer that gathers everything neatly together and resolves all uncertainty, but a place where the questions soften and the edges of understanding begin to fade into something more open. If you think back to where we began, the world felt certain. Objects had clear positions, events followed one another in a steady line. Reality seemed stable, dependable, already formed. And then, slowly, almost gently, that picture began to change. We saw that at the smallest scales things are not always fixed, that particles can exist as possibilities not yet decided. That light can behave like a wave of overlapping paths and like a particle that settles into a single point. We saw that knowing something, simply making information available, can change the outcome of an experiment, that two distant systems can remain connected in ways that do not fade with distance, that the present can influence how we describe the past, not by rewriting it, but by shaping its meaning. We saw that different observers can hold different descriptions of reality, each one consistent within its own perspective. That observation can slow change, and that even the absence of interaction can carry information. And at the largest scales we encountered a universe where information may never truly disappear, where even in the depths of a black hole, the story is preserved in ways we're still learning to understand. All of these ideas taken together do not point to a single simple conclusion. Instead, they form a kind of landscape, a gentle, shifting terrain where certainty and uncertainty coexist, where structure and mystery are intertwined, and perhaps that is the most important realization. That reality is not something that fits neatly into one description. It is not purely deterministic, nor purely random, not entirely objective, nor entirely dependent on observation. It is something more subtle, a process, a relationship, a quiet unfolding where possibilities become experiences, where information shapes outcomes, and where the act of interaction plays a role in defining what becomes real. There is something deeply calming in allowing this openness, in recognizing that not every question needs to be answered completely, that the unknown is not a flaw, but a space where curiosity can rest, where understanding can grow slowly without pressure. Imagine once more that quiet lake we returned to. Throughout this journey, at first its surface seemed still, predictable, easy to read. Then, as we looked closer, we saw ripples, patterns forming and dissolving, overlapping in ways that were not immediately obvious. And then, deeper still, we realized that the lake is not just a surface, It is a depth, a space where movement, reflection, and stillness all coexist. Where what you see depends on how you look and from where. Reality, it seems, may be something like that. Not a fixed picture, but a living process. Not a single layer, but many, gently interacting. And our experience, our sense of what is real, is part of that process, not separate from it, not observing from the outside, but woven into it, moment by moment. As you sit with this, there is no need to hold on to every detail. It is enough to feel the overall shape, a universe that is both precise and mysterious, structured yet open, predictable in its patterns yet surprising in its details, and within that universe a place for quiet curiosity, for gentle exploration, for the kind of understanding that does not demand certainty but finds comfort in the unfolding. Perhaps in the end the question we began with, whether reality exists without observation, does not have a single, definitive answer. Perhaps the answer depends on how we choose to frame the question. Reality may not wait for us to look in order to exist, but the form it takes, the way it appears, the patterns we're able to see, these may be shaped in subtle ways by the interactions that bring it into focus. And that is enough. Enough to wonder, enough to rest with, enough to let the mind drift gently through the quiet mystery of it all. And so, we've reached the end of tonight's exploration. Whether your eyes are still open or you're already floating somewhere between waking and dreaming, thank you for being part of this little journey. If you'd like to join me again for more gentle wanderings, you're always welcome to subscribe or share this with someone who could use a peaceful pause. Time has a way of slipping through our fingers, but here, in this quiet moment, it's just you and the soft hush of rest. Sleep peacefully, wherever and whenever you may be.